Hello, this is lecture 9 on time series, and now we're going to discuss ARIMA forecasting model, which is a bit old but really very important for understanding time series. Here my tribute goes to my former colleague from Higher School of Economics, Evgeny Rabenko. We also collaborated in a specialization by Yandex and Moscow Institute of Physics and Technology. It's in Russian, so mostly Russian speakers know this specialization. So currently Evgeny works at Facebook, and thanks him for providing these slides. So we're going to discuss basics of time series and how it's typically done, how forecasting is typically done in econometrics approach. Okay, so formally a time series is just a series. So it's a sequence of values of some feature measured in constant time intervals. And in this graph we can actually build it, easily depict. So it's some average real wages. These are actually monthly average wages in Russia. So you see the definition is pretty simple and straightforward, but even this simple definition implies that some feature is measured over constant time intervals. So if you've got some observations measured in non-constant time intervals, so formally it's not time series. And of course our main task here will be to look into future, to make a forecast. And if we'd like to make a strict definition, so a forecast will be finding a function that describes our future values of y t plus d. So if our time series is measured up to some period t capital, then we're going to predict a value at time period t plus d, and we're going to find a function which gives this prediction based on our values of time series and this d. Well, not a very strict definition, but it's still intuitive. And d here is called forecast horizon. Well, so a small example showing that prediction is really very important. So there is a slight difference between forecasting and prediction. So for basic machine learning models, we typically call it prediction. In time series, when we look into the future, we mostly name it forecasting. So this small example shows how prediction intervals can be really very, very important for forecasting. So there was a threat of a flood in North Dakota, and the city was going, they planned to protect the city with a dam 51 feet high, because they received a forecast that they need 49 feet dam. Well, they didn't consider prediction intervals, and you see they didn't account for non-perfect predictions, so they only had 2 extra feet height in this dam. Well, and so actually the actual flood was 54 feet height, and that led to really enormous damages. 50,000 citizens were evacuated. Well, this is just a real story illustrating how we not only care about predictions, but typically about prediction intervals as well. So a very simple idea for forecasting when we deal with time series will be just a regression. Well, we see that in a simple case, if we just do a simple linear regression, it's not going to work. So in this left upper corner, we see just predicting with this very simple straight line. In the upper right corner, we try to fit a quadratic with time. But still, if we plot residuals, so the differences between predictions and actual values, we see a lot of information in these residuals. So in both cases. either we predict with a linear function or with quadratic or with any polynomial spline, still we'll have a lot of structure in residuals. And typically it says that our model is too simple. So we clearly see some seasonality in this time series, and linear models or splines don't capture this seasonality. So definitely the simplest idea doesn't work here. Let's take a closer look at some more time series. So we've got monthly values of Australian wine sales. So we'll use it to define some key concepts when dealing with time series. So actually the basic idea will be predicting future values with the values that we've seen so far. And it differs very much from typical machine learning setup. So our values will be very dependent from each other. So the main assumption in most machine learning models was that we see some training set, a sample from some distribution, and our observations come independently and from identical distribution. Here, this assumption will not work at all. So here, observations are definitely not identical. So the next value definitely depends very much on the previous one, and we can take a look at correlations between consecutive values. So let's take some value y at time t, and the next value y at time t plus 1. So if we plot if we make a scatter plot of this distribution, so on x-axis we've got values yt, and on the y-axis here we have yt plus 1. So we'll see a nice scatter plot. So we'll see that mostly values are highly correlated, but here in the in the right lower corner, we'll see some values which lay beyond this main diagonal, and this will correspond to Decembers and Januaries. So if we go back to this time series, we'll see that we've got high peaks somewhere and then sudden drops. This corresponds to high wine consumption in December and much lower consumption in January. Okay, New Year, you see, we can actually interpret it really well. And so these Decembers and Januaries will be somewhere in this lower right corner, where we have high values in December and low values in consecutive observation in January next year. We can do the same, but for some values yt and yt plus 2. So, for instance, this yt might be wine sales in December, then we'll plot corresponding wine sales in February. Then January, March, and so on. We see that the dependence is almost the same. Now the distribution is more scattered. And if we continue with that, we'll see, if we take a look at these 3-month differences, we see that now correlation decreases. And the same if we see 4-leg difference, so these differences are called legs, LAG. So in our case, 1 leg is equal to 1 month. So if we further plot these differences, we'll see lower and lower correlation. But suddenly, when we take a look at 12-month differences, we'll see a very high correlation. And this will help us to formalize the idea of seasonality. Again, if we go back to our original plot, we'll, with the naked eye, we see some very intuitive property which we'll formalize as seasonality. So we see high peaks in December's, December 1990, then the next December 1991. So these will all be local maximums of our function, of our time series. So this will be characterized by these plots. So when we suddenly see a very high correlation, if we if we consider 12-month differences between observations. So it will formalize this idea with autocorrelation. So it's in the simplest case, it's a usual Pearson correlation between time series with some lag. Again, lag, this lag. So we'll treat yt, our time series, and yt plus tau. So tau will be this lag. And then we'll just calculate usual Pearson correlation between these observations. So this will be our estimation of this correlation with our time series. So you see, we take a look at these differences, yt minus average of y, and then multiplied by yt plus tau, again minus average value of y. And like in a simplest case of a correlation, if these both values are higher than average, then it will impact positive values of correlation. And if these differences are different, either positive or negative, then it will decrease correlation. So we can easily test it whether this autocorrelation is different from 0. So with a simple student t-test, we can check whether this autocorrelation is 0 or an alternative if it doesn't equal to 0. So we'll see, even with this definition, you might think that we'll observe high autocorrelation for lag equaling 1. Yep. So this will be correlation between a time series and the same time series shifted with one lag. So we expect very high dependency of between consecutive values in our time series. That's why autocorrelation with lag 1 will be high. Then with 2 it will be maybe a bit lower, with 3 even lower, and then if tau equals 12, we'll suddenly see high autocorrelation. And we can build such a plot. It will be called correlogram. So here in the lower part, it will actually plot autocorrelation for different lags. So here x-axis will be lags, 1, 2, 3, and so on. And we'll plot this autocorrelation. So when we have tau equaling 0, we'll have autocorrelation 1. It's obvious, so correlation between time series and itself. And then for tau equaling 1, we'll have some low autocorrelation. For tau equaling 2, the same again, some low correlation. But then suddenly at tau equaling 12, we'll see some correlation almost 0.8, so pretty high. So this is definitely a sign of seasonality. So if we increase and see and treat tau equaling 24, 36, then 48, and so on, we'll see pretty high peaks of autocorrelation. So basically, this will help us to make forecast. So the first idea is that we can use the values of series itself to predict its future values. So some basic ideas about time series is that we can extract some of its properties called trend, seasonality, cycles, and error. So a trend in time series is typically some long-term shift of its expected value. So if we see that generally values are increasing or on the contrary decreasing, this will be called a trend. So pretty intuitive definition. Seasonality will be some fluctuations of our values with a fixed period. Like in our case, we had 12 months seasonality, so actually year seasonality. Cycles, it's going to be something different, so really subtle difference with seasonality. Again, these are some fluctuations, but now they don't have fixed frequency. And actually, this will not help us predicting future values. So such fluctuations might be some economic cycles, maybe solar activity, or something really unpredictable. And now error, like in case of linear models, this will be something unpredictable, just a random component, which we can't model. So some examples of time series. Let's take a look at their properties. We can build these autocorrelation functions to actually examine properties of different time series. And actually these ACF, autocorrelation functions, will depict different properties of time series. So here we depict 4 different autocorrelation functions, and by the look of this autocorrelation function, we can actually see different properties of time series. So the first one was monthly housing sales, and here we actually, well, maybe this is the hardest case. So here we have some cyclicity. So we also have some seasonality, but also we have some sinusoid, actually some cycles. And this is also can be seen on ACF, on autocorrelation functions. We also have some sinusoid here as well. Yeah, sorry, my mouse is not highlighted here. So currently I'm talking about upper left corner, so monthly housing sales. Let's go back to upper right corner. So this is another time series, and now we definitely see a trend here. So overall, the values are decreasing. And if we go to ACF, again, so again upper right corner, we see that when we have a trend, this can be seen with via autocorrelations. So a lot of autocorrelations are really high, and so values of these autocorrelations are slightly decreasing. Now lower left corner, Australian monthly electricity production. Here we have again a very high trend, and again seasonality. And if we take a look at its autocorrelation function, again it's something really very steadily decreasing. So a lot of autocorrelations are really very high. So this is the impact of strong trend in our time series. If you take a closer look, so here in the lower left corner, peaks of these autocorrelations have some fluctuations, some sinusoid maybe. This is actually the influence of seasonality. But we can't see it clear because of a really very high trend in this time series. Finally, daily changes in Dow Jones index. Well, some people are crazy about it, try to see some dependencies here and try to predict it. Actually, this is very close to what it's called Gaussian white noise, so we don't see anything here. So values are spread around 0, and we don't see seasonality, cyclicity, trends, nothing here. And this is depicted with, well, this property can be seen also with ACF, autocorrelation functions. So just at index 0, so here in the lower right corner, we see autocorrelation is 1 when lag is 0, and all others are just very low and almost random. So this dashed blue line will show statistical significance, and well, we'll see that almost all autocorrelations are not significant at all. Some autocorrelations are significant by chance, so actually we need to to account for multiple hypothesis testing. But actually, a naked eye would tell us that we don't see any properties here in this time series. So we can take a look at the plot of the original time series, and also we can take a look at the plot of autocorrelation function, and it will show us properties of this time series. There exist some other approaches like STL decomposition, seasonal and trend decomposition with low S. So if we have original dataset, as here above, this method can detect seasonal components, trends, and residuals. So it's also very convenient. Sometimes we would like to drop seasonality just to make our interpretation clear, more clear. Yes, so for the same time series of average real wages, we can take a look and plot only trend and residuals, dropping seasonality, and it will show us a more interpretable plot of the very same value. Okay, a key component for analyzing time series is stationarity. So a time series is called stationary if its distribution doesn't depend on actually on time. And by distribution we would mean statistical properties of these time series, including mean, standard deviation, and so on. So it's not a formal definition, but still we can detect the cases where we definitely have non-stationarity. So when we have a trend, clearly our average value of time series or its expected value, it's either increases or decreases, then definitely the series is non-stationary. So the definition implies that if we take a look at any time interval, we cannot predict statistics of time series. So the function describing these time series doesn't depend on the time interval that we are examining. And in case of trend, we can definitely say that, for instance, if we have an upcoming trend, so we can definitely say that if we move further on time axis, so if we go to future, then we definitely expect higher values of time series. So trend implies non-stationarity. Seasonality again implies non-stationarity because again, so we can move to the left or to the right on time axis, and we can expect different values due to seasonality. So in case of cycles, it's a bit more subtle again. We cannot guarantee that a series is non-stationary if we have cycles. So cycles are somewhat non-predictable, so we cannot definitely say something about time series if we have cycles. Well, this can be illustrated with examples. If we have 9 time series, we can detect non-stationary ones because of seasonality. Yep, so we've got some beer consumption graphs, electricity consumption, house sales. So all of these highlighted with red are non-stationary because of seasonality. Some of them are also non-stationary because of trend. And these highlighted time series are non-stationary because we've got trend. So trend can be monotonous, like in the lower right corner with electricity. So on the whole time range, we've got a positive trend. Or maybe trend can be local, or even it can change sign, but still it's going to be trend, and the series is non-stationary in this case. A series can be non-stationary because of change in variance. So you see again this lower right graph. we can see that variance of this time series changing is actually increasing. Yeah, so first we have some small fluctuations, and then to the right we've got much higher fluctuations. Again, this is a statistics of this graph, so the variance of this fluctuation, and it changes over time. That's why this time series is non-stationary. And we are left with a couple of more stationary time series. So one of them is actually this daily Dow Jones index changes. Okay, when we do forecast, we typically examine residuals. So these are differences between actual values and predicted ones. And we typically analyze these residuals both in terms of different metrics, and we also plot graphs of these residuals to analyze whether we don't have any information left in these residuals. This picture shows a typical time series cross-validation scheme. So the main principle is to leave our validation set in future as compared to the one that we used for training. Okay, and so we have some requirements for these residuals. So some necessary properties of these errors are unbiasedness. So we expect these residuals to be close to zero. So this graph shows some time series, and it's simple prediction using moving average. So in this case, residuals are slightly more often negative than positive, and this is actually not a good property. We would like residuals to be spread near zero, and actually we can test it with the same student t-test. Then we would like to have no autocorrelation in residuals. So again, if we see autocorrelation in residuals, it will mean that we have some information left in errors, and we can again analyze it with autocorrelation functions. In this case, we've got some time series and prediction. In the middle, we've got residuals, and there is some information left in residuals, actually seasonality. And autocorrelation function will show us that we are left with some seasonality in residuals. That means that we didn't capture all seasonality in our original graph, and actually we can improve our model. Then we would like our residuals to be stationary, and again we can analyze them with the same plots. We can plot residuals, and you see here we've got increasing variance in these values of residuals. Again, non-desirable behavior because so ideally residuals would be just white Gaussian noise. And finally, we would like to check normality of residuals. This can be done with QQ plots. So we build theoretical quantiles of normal distribution and compare it with sample quantiles estimated with our given residuals. So finally, checking these residuals, we would use some Wilcoxon or student t-test to check whether the average value of residuals is equal to zero. Then we'll do visual analysis for stationarity, and we've got some tests for that. Then we'll take a look at parallelogram and autocorrelation function to check uncorrelatedness. So we don't like our values of our residuals to be dependent on the nearby values. And there are some other t-tests, other tests like Leung box test for that. And finally, we'll check normality of residuals visually with QQ plots, or maybe Shapiro-Wilk test, the most famous test for normality. Okay, so some more information about these tests. Actually, I'm going to skip it. These are a bit complicated, and you can actually find some information on Wikipedia. So these are really specific statistical information on these tests. Okay, so typically analyzing time series starts with a visual plot, and first thing we'll try to do, we'll try to make some transformations to this time series to convert it into a stationary series. So in case of a stationary series, we'll be able to actually predict its values. So the first thing to do is to remove this dependency of observation variance on time. So here to the left we see our original graph, and again it's monthly electricity consumption, and we see that the variance of these fluctuations increases over time, and we can introduce some simple transformations to actually make this variance of fluctuations a bit more uniform. A very simple thing to do will be just to take a logarithm of our original series, and now this variance will be more uniform. A more general approach is to use Box-Cox transformation, so it's parameterized, and it can be either polynomial or logarithmic, depending on the value of this parameter lambda. And so typically you just tune this parameter to make your variance, the variance of these time series, more stable. So you first transform your time series with this transformation, and then when you do prediction, and then you need to make an inverse transformation to go back to your original scale. By far the most common approach to make time series stationary is to differentiate it. So differentiating in this case means just numeric differentiation. That is simply taking differences between consecutive observations. So if we had this yt time series initially, we can go to yt prime, which is comprised of differences yt minus the previous value yt minus 1. Well, it almost in all cases removes trend. So because we go to these consecutive differences, and we can apply it multiple times. So we'll have a basic theorem that we can make nice predictions for stationary time series. So this will be in a couple of minutes. So for now we do different transformations for our original time series to actually get stationary time series. And differentiation is by far the most efficient way to actually end up with a stationary time series. So if we take a look, so here in the upper left corner we've got daily values of Dow Jones index, and below we have it's actually the same time series but differentiated. So from these daily values we go to daily differences, and you see this original time series Dow Jones index has some properties, has a trend, so first positive trend, then negative trend, then maybe again positive, and we can analyze it with autocorrelation functions. But differentiating this time series just says that now we don't have such properties, and we get a stationary time series. Okay, this KPSS test actually confirms that the original Dow Jones time series graph was non-stationary, but now when we did differentiation we got a stationary time series. We can do the same but for seasonal differencing. So it will be the same, but now we'll go to these paired differences between yt and yt minus s, where s is going to be our estimated season lag. So in case of wine sales, we'll go to differences between wine sales in December 2000, let's say 18 compared to the previous one, December 2017, and so on. So we'll take these 1 year differences and we'll get a new time series. And in general, this will be parameterized by this S, our seasonality, which we'll estimate just visually. Okay, so one more graph, and if we take monthly differences, so then we'll come up, eventually we'll come up with a stationary time series. So here, the upper one is original graph, then we applied log transformation, and in the bottom we see these monthly differences. And again, the test confirms that first two are non-stationary, and the last one, the bottom time series, is actually stationary. So the main idea behind actually forecasting will be to use previous values of time series to predict the next one. Okay, sounds obvious, but now it's going to be formally a model. It's an autoregression model. So we're going to predict yt as a linear combination of some constant alpha, then the previous value yt minus 1 with some coefficient phi1, and then we take overall p components, so p previous values of our time series with coefficients phi1, phi2, and so on, phi p. And then we are left with some epsilon t, some error which we cannot model. So this will be autoregression model with this parameter p. So just a linear combination of last p values with some random noise component. So this is the first idea. The second idea is a bit more involved, so a bit trickier. Let's plot random noise. So these are values generated from Gaussian distribution, and one axis is just index, and another axis is the values of these noise. And let's apply moving average to these values. So if we take two consecutive time points and calculate their average with red, so we'll actually end up with some intermediate values, some averages between nearby dots, and we can actually visualize it. We can do the same for 3 consecutive time points, then for 4, and so on. And the more dots we have, the more points we use to estimate this moving average, the closer our red graph will be to actually stationary graph. And now's the trick. So actually suppose this red graph is our initial time series. Then we can actually model it as an average of some random noise. So this is a bit more tricky, but it provides some another idea how we can model yt, and so how we are going to predict the next values. So if we model yt with q values of random noise, so these epsilon t minus 1, and so on, so we can also have some prediction just with the values of these epsilons. So these epsilons are going to be errors of our models. So the idea is that we can use errors, so how bad our model was at previous timestamps, to predict next values. So this is something a bit smarter, and this model is called moving average with the parameter q. Now we can combine these two approaches and we get autoregression and moving average. So this is ARMA model with parameters p and q. So we just combined the previous autoregression approach and moving average approach. And finally, ARIMA is the same for a series which has been differentiated d times. So we introduced one more parameter d. It's how many times the original time series was differentiated. And so I here stands for integrated. So we'll build an ARMA model for a differentiated graph. Then we need to apply inverse transformation. So in this sense, it's integrating. Okay, so finally we'll use seasonal ARIMA. So sometimes it's called SARIMA, S-A-R-I-M-A. But typically by ARIMA, they just mean that it can be seasonal. Okay, so we're going to detect seasonality in our graph, and we differentiate our original time series, and we apply this ARMA model, A-R-M-A, to a differentiated graph. And now we can take P capital last seasonal components. So it means if our season is 1 year, then to predict the next value, we'll use the value of this time series 1 year ago, 2 years ago, 3 years ago, and so on, and then P capital years ago. And the same for Q capital moving average components. So we'll include in our model the error 1 year ago, 2 years ago, and so on, Q capital years ago. So this is going to be a SARIMA model, and now it has 6 parameters. So we'll include seasonal components, and so small p, d, and q stand for actually p value. Okay, so we've got p values of the time series to make a prediction. We've got q components of errors to improve the prediction. Small d is we apply to differentiation d times, and the same capitalized just stand for the same but for seasonal components. And this we'll call just ARIMA. Okay, so there are a lot of parameters here. This constant value alpha, this phi and theta for time series components and their errors, and then these 6 hyperparameters d, q, and p. With first 3 ones, alpha, phi, and theta, it's pretty simple. We'll just use ordinary least squares just as in a typical regression problem. We'll minimize squared error between actual values and predicted ones. This d, so small d and capital D, this will be analyzed actually visually. So we'll differentiate our time series as much as needed. For this Q and P parameters, so a typical approach is to use information criteria. The most popular is Akaike criterion. So basically it's a substitute for cross-validation. So we'll apply maximal likelihood principle, and the idea is to have large likelihood, so that our model describes time series very well, but at the same time we would like to have as less as possible parameters in our model to do so. So again, it's a balance between model capacity and model complexity, and it's nicely expressed in this Akaike criterion. So you see we've got likelihood, and we take its negative logarithm. So we would like this value to be low for likelihood to be high, and at the same time K here is the total number of parameters in our model, P capital plus Q capital plus lower P and Q, and for some reason +1 is also needed. We'll minimize this AIC criterion to actually balance between model complexity and its ability to explain data that we see. Okay, so there are some techniques to tune these parameters. These are, you see, these are hyperparameters. So we'll try different combinations, basically we can try lots and lots of values. But there are some heuristics how you can limit your values of small q and q capital. This can be done with autocorrelation function, this ACF plot. So with the help of this plot, we can define initial values for q capital and for q. So for q capital, we'll take the number of last significant seasonal lag. So if we have 1 year seasonality, so we'll take a look at autocorrelation function, and we'll take a look at number 12. So we'll have a significant value of autocorrelation for actually for 12 months. And so that's why we'll just pick Q equal to 1. Lower Q will stand for less significant non-seasonal lag. So here we just analyze ACF and see how many values of autocorrelation we see significant. So for tau equaling 1, we see significant autocorrelation, and for tau equaling 2, we also see significant autocorrelation. So then we'll set Q to be equal to 2. So these are heuristics. So actually, it's just to save your computational time. What we'll actually do, we'll try different combinations of all these hyperparameters, train model, and with help of Akaike criterion, we'll choose those combinations that lead to the lowest value of AIC. Okay, so the same can be done for P. This can be estimated with a partial autocorrelation function. It resembles autocorrelation function, but it's so it's actually autocorrelation. But if we account for our prediction, so if we take a look at our predictions, which have a hat here, and we go to the differences between actual values and these predictions, we can again analyze autocorrelation in such time series. And partial autocorrelation will explain us actually these correlations of our residuals if we actually subtracted our prediction. Okay, and these values for P can be estimated with a plot of partial autocorrelation. So by the same token, we can pick P capital here, so the number of last significant seasonal lag, and small p as again the number of last significant non-seasonal lag. Okay, so how do we do forecasting with ARIMA model? So first we take a look at the plot. We find some particular properties of our graph. We detect seasonality. So if needed, we apply variance stabilization with just with a logarithm, or generally with a box-Cox transformation. And also we detect seasonality. So we see either we've got weekly seasonality or daily or maybe hourly. And so then we select appropriate D and D capital to actually find differences. Yep, so to differentiate our time series. And we also built visual plots to check whether with these transformations we are left with a stationary stationary time series. Okay, and then we analyze autocorrelation and partial autocorrelation plots to initialize values of all these hyperparameters, and then we train model comparing their values of AIC criterion and select the winner. Then we analyze residuals. We check whether residuals are unbiased, whether they are uncorrelated, and whether they have normal distribution. And we see, again, visually whether there is some information left in residuals. If there is, then our model maybe is not too complex. Okay, I don't see it in these slides, but there is a theorem that if we have ARIMA, then every stationary time series can be expressed as a member of this ARIMA family. So there exists some parameters P, D, and Q that can describe a stationary time series. So this Wald theorem, and it actually explains nice theoretical properties of the ARIMA model. So Wald theorem, W-A-L-D. Okay, so how do we actually do forecasting with ARIMA? So now it's a bit more involved than in case of just classification or regression. So we see this in the first row. It's how we model YT. So we estimate these parameters alpha and alpha, phi, and theta. So we've got hats here because we estimated their minimizing mean squared error between real values and predictions. Then if our highest value in our time series is t capital, then we're going to make a prediction for t capital plus 1. So here we replace t with t capital plus 1. And so for prediction, we'll need our values, y, t capital, and so on. But we also need actually values of the error of our model at times epsilon t plus 1, epsilon t, and so on. Well, so to make a prediction, we'll need an information about the error of our model in future. Well, so we can provide that. In the best scenario, we just assume that these future errors are going to be zeros. And so we throw away this term epsilon t plus 1. And we are left with these epsilons in previous time steps. Okay, we can just replace these errors with residuals. Okay, so now we'll have epsilons with hats. So these are actually residuals. Okay, and now if we want to make a prediction for the horizon 2, so to do a prediction for t capital plus 2, we'll use the value of our prediction for y t plus 1. So in some sense, our predictions will be chained. So to make a prediction for value t plus 2, we'll need the value of our prediction for t plus 1, and so on. So we just replace these values with forecasts. Okay, so we also can build prediction intervals. So there are some analytical formulas for that. So actually this can be also simulated instead of analytical formulas. So typically we not only do a prediction, but also we do it with time intervals. So actually to get some idea of how confident our model is with its prediction. Okay, this is about R. So to be honest, time series analysis is much better done in R than in Python. And at some point, if you do a lot of time series, you'd better switch to R. You just find that much more methods are implemented originally in R. Okay, there are some features which cannot be modeled with ARIMA. So if we see some anomalies, non-trivial dependencies, which are not seasonal, we can see that ARIMA will fail to model them. In this example, these are electricity consumption drops in Turkey. And this is due to, on holidays, people have much more free time and then they consume electricity less. But in this plot, we see that these drops are non-seasonal. And the reason is that in Turkey, they have another calendar, Islamic, and it's a bit shorter than a year. A year in this calendar is a bit shorter than in Gregorian, and this causes some inconvenience. Actually, ARIMA fails to model this. We can actually extend ARIMA with some hand-created features. So if we just take a combination of linear regression with some features X, and we also use ZT as the whole SARIMA model that we just described, this will be called SARIMAX, so extended. The idea is that we can actually add handcrafted features to our models. So if we go back to this graph, we'll just create a binary feature, so whether it's a holiday or not. And this basic model can be actually extended with handcrafted features. You'll just underline whether it's a holiday, so you can actually customize your time series prediction with any events that you're interested. So this can be some features like whether it's summer or winter or whatever. So this was basic ARIMA model, and it's good for understanding. So there is nice theory behind ARIMA, but however, in practice, it requires a lot of visual analysis, a lot of handcrafted work. So you've seen this pipeline, how we actually analyze time series with ARIMA. It's a little bit involved, and moreover, fitting all these parameters takes a lot of time. It turns out that creating these features sometimes work better, and sometimes even you can use basic machine learning models with handcrafted features. However, ARIMA is still perfect if you've got scarce data. So if you have some 70 observations or 100, so still ARIMA would be perfect. But if you need to predict hundreds or thousands of time series, you would better go for other approaches, like very simple models like moving averages or exponential smoothing, or Facebook Profit also offers some simple prediction which can be scaled, which can be applied for lots and lots of time series. So one more advantage of ARIMA is that it basically, so first it's very good for small data sets, and second it's typically more accurate than other approaches. So it requires a lot of effort in terms of analyzing the graph and tuning hyperparameters. But in the end, because of all these hyperparameters and because of nice theoretical foundation for this model, it can be more accurate than competing approaches. Now let's take a look at the implementation of this whole pipeline. So how do we actually analyze analyze time series with ARIMA. One moment. Okay, looks good. As an example, we'll take a time series on accidental deaths in US. There are several nice sources for different time series. A lot of time series is analyzed in econometrics and in trading. So here's just one more time series that we're going to analyze. Well, somebody gathered some statistics. The number of accidental deaths during the period from 1973 till 1979. Okay, with our naked eye we can detect some seasonality here, and we'll try to predict the values for this time series with ARIMA. So in Python this is implemented in stats models package, but indeed it's better to go for R if you're going to do a lot of time series in your life. Okay, so here for this graph we can first do STL decomposition, seasonal and trend decomposition, and we're going to analyze stationarity. So in this graph we can detect a trend, so we can see that overall the values are decreasing. We can detect seasonality here as well. And then we are left with residuals. Okay, so first what we do, we perform different transformations to actually turn our time series to a stationary one. So first we differentiate our time series seasonally. So with our naked eye we see yearly seasonality in our graph, and from original graph we'll go for its differences. In pandas you can shift values to some value. In our case we shift values of our time series with 12 months. That means that we will end up with yearly differences for this time series. Okay, and so in Python we've got Dickey-Fuller implementation of this test for non-stationarity. So the Dickey-Fuller test actually checks non-stationarity. So in this case, when p-value is high, like in the previous one, it does not reject the hypothesis that our time series is non-stationary. Now, after such transformation, it rejects this hypothesis, saying that probably time series is stationary. But still, if we do STL decomposition, we're still left with a trend. That implies that we didn't drop all of non-stationarity in our graph. We are still left with a trend. So we can apply differentiation once more. Now, instead of seasonal differentiation, we'll just do a typical one, a monthly, shifting values just 1 month. Now, Dickey-Fuller criterion says that our graph is stationary, and if we do decomposition into trend and seasonality, we indeed see that the time series is stationary. So we'll do model selection. So for that we'll build ACF and PACF plots. So autocorrelation now shows that maybe some seasonality is left, well, we see that the first autocorrelation is significant, then maybe number 12 is significant, but all others are non-significant. Well, with partial autocorrelation, I think I encountered a bug here because partial autocorrelation cannot be higher than 1. But still, we see that some values are non-significant. So most of the values are non-significant, and only first two ones significantly differ from 0. And so we can initialize these values of Q and P, and then we'll do actually hyperparameter search in some ranges of these values. Okay, so with the first plot, we estimated Q's. So Q capital was 2, and lower Q was 1. So lower Q was 1 because we actually see only the first significant autocorrelation at the first leg, when tau equals 1. Well, okay, I'm not sure about Q capital, whether it can be equal 2 or 1. But the general idea is that we are going to restrict the search space. So if we increase these values, nothing wrong happens, only that we are going to do more computation. Okay, so we'll define some ranges for which we'll tune P and Q. So we've differentiated the whole time series once seasonally and once usually, non-seasonally. So that's why both D and D capital will be equal 1. And then we'll be tuning all these P's and Q's. So we'll have 27 combinations of parameters. And now we'll have some code to actually list all the values in this hyperparameter list, and we'll train SARIMAX model with the values of our time series, and we'll pass all these parameters that we have. Well, some combinations of parameters are wrong, and so we'll make a try and accept block for that. And we'll calculate AIC criterion for the model, and we'll choose the best model according to AIC criterion. Okay, in this case, we've got only around 70 observations, so our time series is really very small. But for larger time series, you'll see that this step, actually enumerating all possible combinations and training models, this will possibly take some 20 or 30 minutes, depending on actually the size of your time series. Okay, so we can print combinations of our parameters with their AIC values, and we choose combinations with the lowest value of AIC. So this means that we, with these parameters, we use actually as few parameters as possible to achieve appropriate likelihood. So actually appropriately low prediction error. We can print summary of this best model. So those who've got some experience with R can actually detect that this is stolen from R, just a Python variable, Python variant of this interface in R. Okay, it can say us that we've got a SARIMAX model. We are left with P equaling twice. So to make a prediction, we'll use two previous values of this time series. We differentiated once. So this is lower D, stands for differentiation. We're not going to use model errors to make a prediction. And these are P, D, and Q capital. So we're going to use seasonal errors, and we once differentiated our time series seasonally. That's why we've got 1 here. And 12 is a parameter of our seasonality, So we've got yearly seasonality in our graph. Then it shows the number of observations, 72, log likelihood, then values of different information criteria, and so on and so on. So lots of statistics, different results of applying various statistical tests, coefficients of our linear models, and so on. Now we're going to plot residuals. Okay, maybe some error depicting the plot here, but it says that students' criterion confirmed that residuals are mostly zeros here. So a student's t-test will check a null hypothesis that average value is 0 and an alternative that it's different from 0. And now it got large p-value. That means that we don't reject the null hypothesis. So the average value of the errors are mostly 0. And Dickey-Fuller criterion confirms that residuals are stationary. Now we can make a plot how well our prediction fits to time series. So in blue we have actual values, and in red we've got a forecast. And we see that the model behaves really very reasonable. You see in the left part we've got only actual values but not forecasts, because we differentiate our graph once monthly and once yearly. That's why we can start making predictions only from the 13th month. Yep, so to make a prediction we need to know the value last year and the value of this time series 13 months ago. Okay, and now we can do a forecast, and again we see that our model captures seasonality and trend really well. So you see that the prediction in red here looks really very nice. So it will be pretty challenging to make the same prediction, let's say, with the linear model. It's still possible. You can extract different features from this time series and to make a prediction with a linear model. But still, for such a small time series, it's very well done with an ARIMA model. Okay, so if you go to mlcourse.ai, so here we have two parts about time series. So the first one is basics, and the second part is about Facebook Profit library. So some more information about ARIMA can be found in this first part, but it starts with simple approaches, predicting with moving averages. It also covers some metrics of prediction quality. So go through that. If you want your prediction to be really very quick, and if you'd like to make predictions for lots and lots of time series, just start from simple models, moving averages, like here, or exponential smoothing. And finally, this notebook covers extracting features and making predictions with just models that we're used to, with linear models or even XGBoost. And Facebook also made its attempt to make a simple forecasting model, which can be scaled to different problems and to lots and lots of time series. So, in a nutshell, Facebook Profit forecasting model has three components. So the prediction is done with a trend component, seasonality component, and holidays. So there are different simple models to actually account for G, for trend, for seasonality, and for holidays. So for trend, by default, they use a logistic growth model. So it's just a typical sigmoid as you know, only that we can tune it's called its capacity, the largest value of sigmoid. We can tune growth rate and an offset. So if you plot a sigmoid and if you can allow for its steepness and its maximal value, this can actually model a lot of effects very nicely. So if you've got some upcoming trend, which then actually asymptotes some maximal value, this can be modeled with this logistic growth model. And so in this G component, this trend is by default modeled with this logistic growth function. Seasonality is modeled by another models, and by default Facebook Profit builds one hot encoded these dummy variables for days of week, and it also applies some Fourier analysis to model long-term yearly seasonality. Then it's convenient that Facebook has included different holidays, even some irregular holidays, some schedules, some Black Fridays, which is very handy for consumption prediction. And you can also pass your custom list of events, which is indeed very handy. Here in demo assignments, we provide some more examples of applying Facebook Profit and ARIMA. So I'll cover here only Facebook Profit. As you can see, it's pretty straightforward to apply. So in practice, it's much simpler to use than ARIMA model, but it can be less accurate in the end. So here we deal with a data set on the number of articles on Wikipedia about machine learning. The data set is pretty simple. So date and the number of papers about machine learning. And if we predict it with Facebook Profit, so we'll first set a date. So we'll have a date index. We can make a plot. And you see, with Plotly, we have a very nice plot. We can actually detect seasonality here. We've got some outliers as well, some extremely high or extremely low values. But overall, the dependency seems to be easy to predict. With Facebook Profit, we first import it. And then we'll set a holdout set. 30 observations will be left as a holdout set to actually check the prediction. And we need to specify a certain format for the data set to make a prediction. Well, this is indeed not very convenient. So you need to name this data index as DS and your values as Ys. And then our training set will be all the data we have, apart from these 30 observations as a validation set. And now it's almost as simple as sklearn's fit predict. We initialize the model and then feed it to our data. And we then create a future data frame. So it's going to be just a data frame with time indexes, and we make a prediction. Now we have a lot of information. So if we depict this forecast, so we see that we've got a date index, and Facebook Profit analyzes separately trend. So we've got this column with trend. And then we'll have different terms like lower values for trend, upper values. Then we'll have prediction interval, this y hat lower and y hat upper. And we'll also have some weekly trends, different multiplicative terms. Okay, so finally to the right we'll have y hat, the actual prediction. And now we'll see that we've got some prediction. Well, we've got some questions to check whether you implemented this right. Okay, we can plot the forecast just with our model.plot. Well, again, we see that it behaves pretty reasonably. So we cannot model outliers, of course, but still we capture seasonality pretty well. So from this model, we can also plot trend and seasonality components, which is also very handy. And now we can actually check with this validation set, we can compare true values and predictions, and we can calculate, for instance, mean absolute error. So in our case, it's 600. If we calculate the same but in percent, so it's about 34% error, which sounds pretty reasonable. Okay, you can also experiment with ARIMA. Now I'm not covering it, but for this time series, you'll see that this time tuning hyperparameters will take much longer. So in this case, about 8 minutes. And it will definitely need much more work to do. In the end, we'll see that both models make a reasonable prediction, and you can actually compare errors for Facebook profit and for ARIMA models. Well, if you were to predict the same but for different topics, so let's say here we picked only machine learning, but suppose you would need to predict the number of papers for quantum mechanics, for mathematics, and all other possible sections on Wikipedia, then you'll definitely go for some simple models like exponential smoothing or Holt-Winters or everything that is covered in the first part. But you're not going to do ARIMA predictions for that because it needs a lot of handy work. Okay, so in a nutshell, it was an introduction to time series, and our next topic is gradient boosting. We again switch to machine learning. So gradient boosting is important because for your real-world data, if you don't deal with images, audio, or large collection of texts, so most probably gradient boosting is will be the best performing algorithm. And also here in the first part, I didn't cover this approach with engineering features and then passing these to XGBoost. But I also encourage you to study this first part. So it's about feature extraction. And again, it utilizes gradient boosting for time series as well. So it also was shown to be useful. Just come up with nice features and go for XGBoost. Okay, again, here in the end we XGBoost all the things, so a lot of memes about XGBoost. This can also be applied to time series, and so next time we are going to cover the basics of gradient boosting and how you actually tune it for your data. Okay, good luck.